phasor is a mathematical representation of a sinusoidal function that varies in both magnitude and phase. It is typically used in electrical engineering and physics to analyze alternating current circuits and systems. Phasors can be represented graphically as vectors. The magnitude represents the amplitude or peak value of the sinusoidal function. The angle represents the phase, or the time shift between the phasor and a reference point, which is usually 0 degrees. Phasors are often expressed in complex notation, where the magnitude and angle are combined into a single complex number. The real part of the complex number represents the cosine component of the sinusoidal function, and the imaginary part represents the sine component. Phasors simplify the analysis of alternating current circuits by reducing the number of variables involved. They allow for the combination of multiple sinusoidal functions with different frequencies and phases. They provide a convenient method for representing power and energy in alternating current systems. Phasors are used in various applications, including first the analysis of alternating current circuits for impedance, power factor, and so forth. Secondly, power system analysis for load flow, stability, and so forth. Thirdly, antenna theory. Fourthly, signal processing. Fifthly, acoustics. To further elaborate, consider the nature of alternating current. Unlike direct current, which flows in one direction, alternating current changes direction periodically. This change is typically sinusoidal, meaning it follows a sine wave pattern. Because of this constantly changing nature, analyzing alternating current circuits directly using time-domain equations can become quite complex, especially when dealing with multiple components like resistors, inductors, and capacitors. Each of these components reacts differently to alternating current, introducing phase shifts between voltage and current. This is where phasors come into play. They provide a way to represent these sinusoidal quantities as constant vectors in a complex plane, making the analysis much simpler. Imagine a rotating vector in a two-dimensional plane. The length of this vector represents the magnitude of the sinusoidal function, and the angle it makes with the horizontal axis represents its phase. As the vector rotates, its projection on the horizontal axis traces out the cosine wave, and its projection on the vertical axis traces out the sine wave. This rotating vector is essentially a phasor. By representing sinusoidal voltages and currents as phasors, we can use algebraic techniques to analyze alternating current circuits, just like we do with direct current circuits. For example, impedance, which is the alternating current equivalent of resistance, can be represented as a complex number using phasors. The magnitude of the impedance represents the opposition to current flow, and the angle represents the phase shift between voltage and current. When analyzing a series alternating current circuit, we can simply add the phasor impedances of each component to find the total impedance of the circuit. This is much easier than trying to solve the differential equations that would arise from a time-domain analysis. Phasors are also essential in power system analysis. In a power system, we have numerous generators, transformers, and transmission lines, all operating at the same frequency but with different magnitudes and phases. Phasors allow us to represent these quantities as vectors and analyze the flow of power through the system. For example, load flow analysis, which is used to determine the voltage and current of various points in the power system, relies heavily on phasor techniques. Similarly, stability analysis, which is used to ensure that the power system remains stable under various operating conditions, also uses phasors. In antenna theory, phasors are used to analyze the radiation patterns of antennas. An antenna radiates electromagnetic waves, and the strength and direction of these waves depend on the phase and amplitude of the currents flowing in the antenna elements. By representing these currents as phasors, we can calculate the far-field radiation pattern of the antenna. This is important for designing antennas that can effectively transmit or receive signals in a desired direction. In signal processing, phasors are used to analyze and manipulate signals that vary in time. For example, Fourier analysis, which is used to decompose a signal into its constituent frequencies, relies on the concept of phasors. By representing a signal as a sum of complex exponentials, which are essentially rotating phasors, we can analyze its frequency content and filter out unwanted noise. In acoustics, phasors are used to analyze sound waves. Sound waves are also sinusoidal in nature, and their properties can be represented using phasors. For example, the superposition of two sound waves with the same frequency but different phases can be easily analyzed using phasors. This is important for understanding phenomena like interference and diffraction. The use of complex notation for phasors is not just a mathematical convenience. It has a deep connection to the underlying physics of alternating current circuits. The complex exponential function, which is used to represent phasors, is a solution to the differential equations that govern the behavior of alternating current circuits. This means that by using complex notation, we are essentially working with the natural language of alternating current circuits. Furthermore, the real and imaginary parts of a phasor have a physical interpretation. The real part represents the component of the sinusoidal function that is in phase with the reference, while the imaginary part represents the component that is 90 degrees out of phase with the reference. These two components are often referred to as the in-phase and quadrature components, respectively. In summary, a phasor is a powerful tool for analyzing sinusoidal functions, especially in the context of alternating current circuits and systems. It simplifies the analysis by representing sinusoidal quantities as constant vectors in a complex plane. It has applications in various fields, including electrical engineering, physics, antenna theory, signal processing, and acoustics. The use of complex notation for phasors is not just a mathematical trick, but a reflection of the underlying physics of alternating current circuits. Consider a simple alternating current circuit consisting of a resistor and an inductor connected in series to a voltage source. The voltage source produces a sinusoidal voltage with a certain amplitude and frequency. The resistor opposes the flow of current, and the inductor opposes changes in current. Because of the inductor, the current in the circuit will lag behind the voltage by a certain angle. To analyze this circuit using phasors, we first represent the voltage source as a phasor. The magnitude of the phasor is equal to the amplitude of the voltage, and the angle of the phasor is equal to the phase of the voltage. Next, we represent the impedance of the resistor and the inductor as complex numbers. The impedance of the resistor is simply equal to its resistance, which is a real number. The impedance of the inductor is equal to J times its inductance times the frequency, where J is the imaginary unit. We can then add the impedances of the resistor and the inductor to find the total impedance of the circuit. The total impedance is a complex number with a magnitude and an angle. The magnitude of the total impedance represents the total opposition to current flow in the circuit, and the angle represents the phase shift between voltage and current. Finally, we can use Ohm's law to find the current in the circuit. Ohm's law states that the voltage is equal to the current times the impedance. In phasor form, this becomes that the phasor voltage is equal to the phasor current times the complex impedance. We can solve this equation for the phasor current, which gives us the magnitude and phase of the current in the circuit. By using phasors, we have been able to analyze this alternating current circuit using simple algebraic techniques. This is much easier than trying to solve the differential equations that would arise from a time domain analysis. Phasors are also used in power system protection. Power system protection is the process of detecting and isolating faults in a power system. Faults can be caused by a variety of factors, such as lightning strikes, equipment failures, and human error. When a fault occurs, it is important to isolate it as quickly as possible to prevent damage to equipment and to maintain the stability of the power system. Phasors are used in power system protection to detect faults. For example, a common protection scheme is to use current transformers to measure the current flowing in a transmission line. The current transformers produce a signal that is proportional to the current in a line. This signal is then fed into a relay, which is a device that is designed to detect faults. The relay compares the measured current to a threshold value. If the measured current exceeds the threshold value, the relay trips a circuit breaker, which isolates the faulted section of the power system. Phasors are used to improve the accuracy and reliability of power system protection schemes. For example, phasors can be used to compensate for the effects of line impedance. Line impedance is the resistance and inductance of the transmission line. Line impedance can cause the measured current to be different from the actual current at the fault location. Phasors can be used to calculate the actual current at the fault location, which improves the accuracy of the relay. Phasors are a fundamental tool in electrical engineering, enabling efficient analysis and design of complex alternating current systems. Their ability to simplify sinusoidal functions into manageable vectors makes them indispensable for understanding and manipulating alternating current phenomena across various applications.